Hey everyone! So today, let's talk about something we see, drink, and use every single day. Water, H2O. Seems about as simple as it gets, right? But it turns out that familiar bent shape is hiding a really cool chemical secret, one that actually flies in the face of what most of us were taught in school. And the whole mystery really boils down to just one question.
So this is it. This is the heart of the problem. If you took a chemistry class, you probably heard the term sp3 hybridization, and you were told that leads to a perfect tetrahedral angle, 109.5 degrees. But that's not what we actually see with water. So what's going on? Where does that textbook model kind of fall apart?
And here it is, side by side. The textbook says we should get 109.5 degrees, but when we go into the lab and actually measure it, the real angle is about 104.5 degrees. Now, a 5-degree difference might not sound like a lot, but in the world of molecules, that's a huge clue. It's screaming that our simple model is missing something important.
To figure this out, we need a better tool. We need a formula that connects the geometry we can see with the hidden electronic structure we can't. And this is where it starts to get really, really cool.
This is what we need. It's called the angle mixing rule. Now I know, it looks like just a little bit of math, but it is incredibly powerful. Here, alpha is the angle between the two bonds, and n tells you the ratio of p character in that SPN hybridization. It's basically a direct link, a bridge between the shape we can measure and the true electronic nature of the molecule. What's so great about this formula is that it's a two-way street. We could, start with a textbook hybridization like sp3 and use it to predict an angle. But we're going to do something much cooler. We're going to work backward. We're going to take the real, measured angle of water and use it to find out what the hybridization actually is. We're going to let the evidence lead the way. All right, let's play detective. We've got our tool, we've got our evidence, that 104.5-degree angle. Let's plug it into the formula and see what it tells us about water's oxygen-hydrogen bonds. So all we have to do is rearrange our little rule to solve for n. We're going to plug in 104.5 for alpha, find the cosine of that number, and then just calculate -1 divided by that result. And this number, this n, is going to tell us the exact ratio of p character to s character in those bonds. And what number do we get when we do that? We get pretty much exactly 4. So what does that mean? If the p to s ratio is 4, what kind of hybridization is that?
And boom! Here is our first big reveal. The orbitals making those bonds in water aren't sp3 at all. They're actually much closer to sp4. This is a huge departure from what you'll find in most chemistry textbooks.
So what does sp4 even mean? Well, think of it like a recipe. An sp4 hybrid is made from 1 parts s orbital and 4 parts p orbital. If you do the math, that comes out to 20% s character and a massive 80% p character. And that is why this all matters. See, pure p orbitals are naturally 90 degrees apart. So the more p you mix into your recipe, the more you pull that angle down from the ideal 109.5 degrees and closer to 90. So this explains our smaller angle. But that's not actually the whole story. Okay, so we've figured out the 2 orbitals involved in bonding. But the oxygen atom has 4 orbitals in total. What about the other 2? The ones that are just holding those lone pairs of electrons? If the bonds are sp4, what does that leave for the lone pairs? This leads us to a really important rule in chemistry. It's kind of like orbital bookkeeping. The oxygen atom only has one 2s orbital to contribute. So when you add up the percentage of s character across all 4 of its hybrid orbitals, the 2 for bonds and the 2 for lone pairs, it has to equal exactly 1, or 100%. You can't create or destroy s character. So we can set up this really simple little equation. We already know the s fraction for our 2 bonding orbitals is 20%, or 0.2. So we can just plug that number in and solve for the s fraction of the 2 lone pair orbitals.
And when we run the numbers, we get another really interesting result. The lone pair orbitals are not sp4 or even sp3. They are about sp2.33, which means they have a completely different character from the orbitals that are making the bonds.
So if you break down sp2 cubed, you find it's roughly 30% s character and 70% p character. And notice the difference here. That gives the lone pairs a lot more s character than the bonding orbitals had. Let's just put them side by side to make it super clear. The OH bonding orbitals are p richer, and we saw how that pulls the bond angle down. The lone pair orbitals, on the other hand, are s richer, and this difference, this is the final piece of the puzzle. Why?
because s orbitals are held much closer and tighter to the nucleus of the atom.
So now we can finally put all the clues together. We can assemble the complete, accurate picture of the water molecule and solve this mystery once and for all.
So here's the whole story. First, the bonding orbitals are sp4, not sp3. That higher p character naturally makes the angle smaller. Second, to make the orbital math work out, the lone pairs have to become s-richer, or sp2.33. Now, because s orbitals are held so close to the nucleus, those lone pair orbitals are kind of short and fat. They create this big zone of electron repulsion that literally shoves the two hydrogen atoms even closer together. It's both of these effects working together that gives us the exact 104.5-degree angle we see in nature.
So in the end, this just goes to show you that even the most common things around us can hide some incredible complexity. That simple sp3 model we learn is a great starting point, but the reality is always so much more nuanced and honestly, way more interesting. It really makes you wonder, doesn't it? What other simple molecules that we just take for granted are out there, just waiting to show us a deeper, more complicated truth?